I might need some new equipment because, like, I still hadn't figured out, like, you know, how people get smooth streams. It's like every time I watch mine, they're like choppy, and I'm like, my device, you know, is fairly new. I mean, it's not that outdated, but maybe it had to be on like a PC or something like that, something that's more powerful, or I might need to, you know, record them in advance instead of trying to live stream, because it's just, I don't know why it's so choppy. But I hadn't figured out what I need to do to make a better stream. But we'll get there one day. No, I'm ready. Okay. So in the meantime, we'll just kind of keep going what we've been doing. Let me see. So let me check one other thing. Can I check it here? So welcome, gentlemen. Let me see. Hope you had a good weekend. You were able to get some rest and do the things you needed to do. We are at week 10, right? So we have 9, 10, 11. So week 12. So that means not next week, but the following week, we can anticipate exam 3, covering chapter 2, right? So today we're going to work on 2.2 polynomial functions. And as always, this is remote asynchronous, so you know the deal there. If you have questions, feel free to unmute yourself to get my attention, and we could talk about whatever you need to talk about. Otherwise, let's just kind of get into it. Okay, so it's acting up. Let's back up. This one. Okay. So let's see. Yeah, we're continuing chapter 2, polynomial and rational functions. And so today we're going to work on section 2.2, polynomial functions. Some objectives: we'd like to learn properties of the graphs of polynomial functions, determine the end behavior of polynomial functions, find the zeros of a polynomial function by factoring. So this one's big on factoring. Identify the relationship between degrees, real zeros, and turning points, and graph polynomials. Right. This one can be a little bit intense, you know. I mean, I don't know. I feel like that's not a good way to preface it, but let's just kind of take a look at it and see how it evolves. So we have this definition that says a polynomial function of degree n is a function of this form, where n is a non-negative integer and the coefficients that you see are real numbers where a sub n is not equal to 0. All right, let me grab this guy. Ooh, this guy. So a polynomial function, all it is a finite sum of monomials. A monomial is basically one term, where this an is just some real number. Yeah, these are just real numbers where the leading coefficient is not 0, and these powers are non-negative integer exponents. All right. So then a monomial, you have some real number times x to some non-negative integer power. That's a monomial. And then a polynomial is just a finite sum of monomials, right? This is a constant, right? So let's just kind of keep going and kind of get through some of this terminology. The term an x to the n is called the leading term, okay? That pops up a lot. We use that a lot. The number an is called the leading coefficient. And a sub 0 is the constant term. So that's usually just some real number. A constant function f of x equal to a, where a is not 0, can be written as a times x to the power of 0 is a polynomial of degree 0, right? So when we have f of x equals some number other than 0, then we say that's a polynomial of degree 0. The degree of a polynomial is typically the highest exponent on any variable. So the 0 function, when we have f of x equal to 0, has no degree. Because you can write f of x equal to 0 an infinite number of ways. You know, you can write it as equals 0, but that's the same as 0 times x to the power of 9, but that's the same as 0 times x squared, right? So when you have f of x equals 0, we say that has no degree. But f of x equals any other constant, any other real number, we say that has a degree 0. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials, respectively. So cubic is the 3, quartic is 4, quintic is 5. Okay. So this is just like terminology. I feel like once we start working some examples, this stuff kind of sinks in, and just through exposure and repetition, it'll sink in. This expression is a polynomial. The function f defined by f of x equals to that polynomial is called a polynomial function. And then the equation, when you take that polynomial and set it equal to 0, is called a polynomial equation. All right, so we have a polynomial, polynomial function, and polynomial equation. Okay. So common properties of polynomial functions. The domain of a polynomial function is a set of all reals. So if you once you identify a function as polynomial, the domain is all reals. Okay. The graph of a polynomial function is a continuous curve, right? So on the left here, we have an example of a polynomial. It's a continuous curve. There are no holes or gaps or breaks. On the right, we got this gap. So because of that gap, this is not considered a polynomial. Okay. So not only do the graph of polynomials have a continuous curve, but they also have a smooth curve. In other words, there are no sharp corners or edges. So if you look on the left, not only do you have a continuous curve with no holes or gaps or breaks, but you also have a smooth curve with no corners or sharp edges. On the right, though, here's an example of a corner. So because of these corners, this cannot be a polynomial, right? So two main properties of the graphs of polynomials: no holes or gaps or breaks, and no sharp corners. In other words, polynomials are smooth, continuous curves, smooth, continuous, smooth curves. Okay. So then here we're asked to state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. All right. Can someone tell me, is part A, is it a polynomial, yay or nay? All right. So a polynomial is a finite sum of monomials. Notice, this is how many terms does this polynomial have? Terms are things that are added or subtracted. So how many terms does it have? All right. It has 3 terms, so we will call this a trinomial, right? What's the degree of this polynomial?
4.
4, right? So the degree of a polynomial is the highest exponent on any variable. What's the leading coefficient of this polynomial? 5, right? 5 is the leading coefficient is the number in front of the leading term. So what's the leading term?
5x to the 4th power.
5x to the 4, right? The leading term is the term with the highest exponent, right? Sometimes these are out of order. When you're working with a polynomial, it is a good idea to put it in descending power order, right? So the leading term is the term that has the highest exponent or the highest power. The leading coefficient is the number in front of the leading term, you know, yada, yada, yada. Okay, so if you had to guess, is part B, is that a polynomial, yay or nay? If you just had to guess. Right. So I'm going to tell you that it's no, but can you tell me why is it no? What characteristics of polynomials is it violating?
I feel like if it was the graph, it would be like, it wouldn't be continuous. It would skip, like the example that you showed us before.
Okay, that's kind of close. It's something
It's not
similar.
combining the terms.
What is it?
It's not combining the terms.
He was closer with the gap. It's not necessarily a gap, but one property that we said about polynomials is that the domain is all reals. What's the domain here?
Oh, just 1 to 5.
Right. So because the domain is not all reals, then this guy is not a polynomial. If this thing wasn't here, then it would be a polynomial. Right. That was pretty good. Okay. So let's see. And then I think we have all this stuff that we just discussed is typed up here. All right. Okay. So, you know, that was just kind of getting into identifying a polynomial. So let's go a little bit further. So then a power function is a function of this form. It's basically like f of x equals a monomial. It's called a power function of degree n, where a is a non-zero real number and n is a positive integer, right? Okay, so a power function. Some real number times x to some non-negative, or x to some positive integer. Okay. So say we're considering power functions of even degree. So we have this power function, and if the degree on x is even, so if we're saying x is some even power, then what if we consider negative x to an even power? If we consider negative x to an even power, an even number of negatives goes back to positive, right? If we multiply. So then f of negative x equals f of x, all right? So I think we talked about this before, but that's the definition of a function being even. When we evaluate f of negative x and we finish with f of x, that's the definition of a function being even. So when a function is even, that means we have symmetry with respect to the y-axis. That means you can fold it along the y-axis, and the left-hand side is a mirror image of the right. Okay. So the graph of y equals x to the n when you have an even power is similar to the graph of y equals x squared, right? So y equals x squared is a U-shaped curve. If we're dealing with a power function to an even power, the graph is going to be similar to that U shape. Okay. All right. Hopefully that was okay. So in the previous example, we looked at where the exponent was even. So then now we want to see, well, what happens when the exponent is odd? Okay. So same kind of premise or preface. Let me see the time. Let me check Zoom real quickly. See if we got any stragglers. Okay, we got 2. Okay, cool. Let me get these gentlemen. Okay, got this one. This one. All right. So I think that's good. Should be getting in there. All right. So now again, we're looking at when the power function, but it's to an odd power. So now when we say negative x to an odd power, an odd number of negatives is ultimately negative, right? So negative x quantity to the power of an odd number, you can basically factor out the negative. So it's going to be negative times, it's going to finish like this, right? So when we evaluate f of negative x and we finish with negative times f of x, that's the definition of a function being odd, okay? So remember, even was f of negative x equals f of x, but odd means f of negative x equals negative times f of x, okay? Even when a function is even, that means we have y-axis symmetry. When a function is odd, that means we have origin symmetry, all right? So origin symmetry is like whenever you have x comma y, you also have negative x comma negative y. So all the points are equidistant and symmetric about the origin. So again, it's gonna have symmetry with respect to the origin. The graph of this power function when the power is odd is similar to x cubed, right? So the graph of x cubed is kind of like an S-shaped curve, an S-shaped curve. So then when we have a power function where we're raising it to an odd power, it's gonna be similar to x cubed. It's gonna be similar to that shape. Okay. Let's see. Okay, let's keep going. All right, we're still just kind of building some background here. So now we can take these examples where we had a power function raised to an even power, and we could take the power function raised to an odd power. Remember, the even power was similar to the graph was similar to, oh no, shoot, I did not want to hit that. Okay, I think we're okay. The shape was similar to the parabola. Y equals x squared was a U-shaped curve, so they went off in the same direction. When we did the odd power function, it was kind of like an S, down to the left and up to the right. So we have these 4 cases for in behavior of a polynomial function. So the first case is when our leading coefficient is positive, okay? This is actually missing something. Yeah, this slide is missing something. Right here. So I'll put it in purple so you know that I've added it. When the leading coefficient is positive and our n is even, that's what's missing, all right? So when our n is even and our leading coefficient is positive, even means these tails go in the same direction. And then if the leading coefficient is positive, that really means the right-hand side goes up. So this tells me the right-hand side goes up. This tells me the other side does the exact same thing, okay? Okay, hopefully that's okay. So we saw an example where n is even and the leading coefficient is positive. The next one should be where n is even and the leading coefficient is negative, right? And again, it's still missing n is even. Okay. Oh, well, actually, I think we restricted it to, nope. Yeah. We need to say the n is even. Okay. So when the leading coefficient is negative, notice the right-hand side goes down because n is even. The left-hand side does the exact same thing. So the way I remember this when I'm working with polynomials, once I realize that the polynomial is even, then I know the left-hand side does the exact same thing. Okay. So then now the leading coefficient is positive, but in this case, n is odd. N is odd. Okay. So odd means opposite. So a positive leading coefficient means the right-hand side goes up. If the degree of the polynomial is odd, that means the left-hand side does the opposite. Say that one more time. A positive leading coefficient means the right-hand side goes up. With n being odd, that means the left-hand side does the opposite. So if it goes up to the right, that means it's going to go down to the left. So then the final case is where the leading coefficient is negative. Okay. And again, n is odd. Okay. So if the leading coefficient is negative, that means it goes down to the right. If n is odd, that means the left-hand side does the opposite. Okay. All right. So that's the simplest way that I personally have to kind of organize this information. But what this is telling us, this is giving us a sense of the graph of a polynomial without having to use calculators or anything like that. It's telling us about the long-term behavior. Like basically the further to the right or the further to the left on the x-axis we go, this is telling us how the graph is behaving. Okay. So given this polynomial of degree 3, show that p is approximately 2x squared when the absolute value of x is very large. Okay. Let's see if I can remember this one. Let's see. Okay. So say we start, with this polynomial, right? Which is, we got this guy, 2x cubed plus 5x squared minus 7x. And for this, you can just kind of watch. Like you don't have to, because keep in mind, all the stuff you see me writing, you're going to get a copy of it. This one, I would just kind of listen to the story. So we have this polynomial. Now let's let me see. Let's factor out x cubed from all the terms, right? If we factor out x cubed, for instance, if we factor out x cubed from the first term, we're left with 2. Okay. If we factor out x cubed from the second term, we're going to be left with 5 over x. And then it's going to be 7 over x squared plus 11 over x cubed, right? And you know that this is correct because if you distribute back, you get the original, all right? The 3 loses 1, so you have 2 left, you have 1 left, you have none left, right? So then we want to consider, like, let's say something like, let the absolute value of x go to infinity, right? So as the absolute value of x gets really, really big, what happens to our terms? So let me get a copy and paste. So as we let the absolute value of x go to infinity, then let's see. Okay, let me see if you guys can get it. So say we focus on this term here. If the top stays 5, okay, here, let me see. What's 5 divided by 1? Can somebody tell me that one? What's 5 divided by 1?
Just 5.
Right, okay. What is 5 divided by 10 simplified down to? It's the same as what?
A half.
A half, right? What's 5 divided by 100? What's 100 divided by 5, in other words? It's like
20.
20, right? So that one becomes 1 over 20. Can you tell me 5 divided by 1,000? Instead of 20, we went from a half to 1 over 20. What do you think is the next one? 1 over
200.
200, right? If we did 5 divided by 10,000, it should be 1 over 2,000, right? So notice that as that denominator gets bigger and bigger and bigger, what is this term getting closer and closer to? What number? So as this denominator goes off to infinity, as it gets bigger and bigger and bigger, and the numerator is staying fixed, then this guy is getting closer and closer to 0. Right? So as x goes way off to the right, that term essentially goes to 0. Because the top is staying fixed and the bottom is growing infinitely, then it becomes a smaller and smaller and smaller fraction. So then the same happens with the remaining terms as well. This term tends to 0, and this term tends to 0. So as we let x get really, really big, those fractions all essentially go off to 0. So then this is going to be approximately equal to 2x to the power of 3. All right. So this is just like an example showing that this polynomial, as x goes off to the far right, behaves like this power function. Now we just went through those 4 cases where, okay, let's break this one down. So remember, we just had those 4 cases. The first thing is our n even or is our n odd? Is our n even or is it odd?
It's odd.
It's odd, right? So odd in this context means opposite. Now, with the leading coefficient, is this leading coefficient positive or negative? Positive, right? So with the leading coefficient being positive, that means the graph should go up to the right. And because the degree of this polynomial is odd, that means the left-hand side does the opposite. So if we go up to the right, that means it should go down to the left, right? So what we're saying, long story short, what we're saying is that this polynomial, as x goes off to the far right and the far left, is going to behave like this guy. And so it's going to go up to the right and down to the left. All right. And it's really based on the degree of the polynomial and the leading coefficient. Okay. So then we can take those 4 cases that we had just a moment ago, and we can extend them, moving away from the power function, we can extend them to polynomial functions, right? It's essentially the same thing. It's just you just got to make a minor adjustment for it to fit for polynomials, right? So here's a type version of what we just experienced, right? So notice they factored out x cubed, we got that. So then when the absolute value of x is very large, these terms are close to 0. So then this polynomial is approximately 2x cubed, and that's exactly what we said. Okay. So that brings us to what's called the leading term test, right? And this is basically an extension of that power, those 4 cases for the power functions. So let f of x be some polynomial function. We got our, the leading term is here. We got our, and the leading coefficient is not 0, okay? The behavior of the graph as x goes to positive infinity or negative infinity, in other words, to the far right or the far left, is similar to one of the 4 graphs and is described as shown in each case. The middle portion of each graph indicated by the dashed lines is not determined by this test. So this is the leading term test. This tells us about the long-term behavior of these polynomials. So it's just giving us a little bit of insight into the graph of these polynomials without like calculators and digital graphing devices, right? Without plotting points, right? This one is missing it too. Oh, that's so irritating. So again, this is where n is even. Okay, let me just copy this. Okay. So if we're working with an even polynomial and the leading coefficient is positive, a positive leading coefficient means we go up to the right. if the degree of our polynomial is even, that means the other side does the exact same thing. So we're going to go up to the left. So even means the exact same. Odd means opposite. Okay, for this context. So then if the leading coefficient is positive, it's up to the right. What do we say happens if the leading coefficient is negative? Instead of up to the right, it's going to go down to the right. All right. And our n is, oh, I copied it. Let's just paste. All right. So a positive leading coefficient means we go down to the right. With n being even, that means the other side does the exact same thing, down to the left. Okay. So then we saw the two cases where n was even. You know, a positive leading coefficient, negative leading coefficient. Now we're going to consider where n is odd with a positive leading coefficient. So again, n is odd. Let's just copy that. So a positive leading coefficient tells us we go up to the right. An odd, when the degree of the polynomial is odd, that means the other side does the opposite. So we're going to go down to the left. Okay. And then the last one, the leading coefficient is negative, but n is still odd. Same kind of deal, right? Negative leading coefficient means down to the right. Odd means the opposite. So up to the left. Okay. All right. So, you know, this basically what we're doing is like getting a sense of the graph of these polynomials, like putting together different pieces to get a sense of how these graphs look. You could plot points, but this helps. This comes in handy. I mean, it's just something that somebody noticed, and it's just another way to kind of get a sense of these graphs. We got a solid 10 minutes. Let's keep going. So use the leading term test to determine the end behavior of this graph. Okay. So if we're going to do the end behavior, can someone tell me, is the leading coefficient positive or negative? So is our an, is it positive? Is it greater than 0 or less than 0?
Less than 0.
Negative, right? Our leading coefficient is negative. So it's less than 0. So then what does it tell us is going to happen? It's going to go down to the right. Okay. What's the degree of the polynomial? The degree is what's the degree of the polynomial? The power on the largest power. Go ahead.
3.
3. Okay. Is that even or is that odd?
Odd.
Okay. So we have that n is odd. Let me see. Let's go like this. Let's change this up a little bit. So our an, our leading coefficient was -2, which is less than 0. Our n was what? 3, which is odd. So because our degree of our polynomial is odd, that means the other side does the opposite. So it should go up to the left. So down to the right, up to the left. This doesn't tell us about anything in the middle. It just says as x goes off to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. Right? That's all it tells us is the long-term behavior. So down to the right, up to the left. And you can verify this if you looked at the graph. You'll see it should go down to the right and up to the left. Okay. These are supposed to be, let me fix these. These are supposed to basically be arrows. Let's do like this. Let's fix that. Okay, then I think if I go like this, I feel like it's gonna be a little bit too big. Let's copy. Let's paste. Nope. Undo. Let's paste the image. Let's get rid of this guy. Get rid of that. And we need to shrink this down just a little bit. Shrink it down just a little bit more. Just barely fit. Okay, let's copy that and paste. And so I did it in red so that you know that that's a augmentation I made, because I know that's a typo. That's not a real symbol. That's not anything. It's just, you know, sometimes converting from digital, from one format to another, one platform to another, it doesn't process properly. Okay. So those are supposed to be arrows. Okay, that's fine. Let's see, what's the time? We got 5 minutes. Let me see, use the leading term test to determine the end behavior. Oh, this is one we just did, right? So the degree of a polynomial is odd. The leading coefficient is negative. So this is case 4. It's gonna rise to the left and fall to the right. I think that's what we did, okay? Hopefully that's okay. Let's try another one. Real zeros, okay, real zeros of polynomial functions. So if f is a polynomial function and c is a real number, then the following statements are equivalent. So these three are basically saying the same thing. Let me see, if f is a polynomial and c is a real number, so c is a 0 of f is the same as c is the solution or root of this equation, f of x equal to 0, is the same as c is an x-intercept of the graph of f. The point c, 0 is on the graph, right? So the x-intercept or a solution of f of x equal to 0 or a 0, these are all saying the same thing, just 3 different ways. Okay. So find the zeros of the polynomial function. In other words, you can find the x-intercept or just set each one equal to 0 and solve. I feel like I might need some space. I do want to try to get through this because this is basically factoring. Let me get space. Yeah, I'm gonna give myself 2 pages. Let's go like this. So then part A, we have f of x equals x to the 4 minus 2x cubed minus 3x squared. And then part B, we have g of x equals x cubed minus 2x squared plus x minus 2. Okay. Let's take these guys. And let's work on part A. So if we want to find the zeros, basically what we want to do is say x to the 4 minus 2x cubed minus 3x squared. We want to set that equal to 0 and solve, right? Something like this off the rip, you might want to ask yourself, is there a GCF, a greatest common factor? If you're uneasy with factoring, if you go to our Blackboard page, there in like the handout section, there should be I have 2 documents for factoring. One is like an overview, right? A summary of factoring techniques. And then the other document is going to be an entire chapter devoted to factoring. So you can find some support there. Let me try to finish this one out. So it looks like they all have x squared. So it looks like we can factor out an x squared. If we do that, we're left with x squared minus 2x minus 3 equal to 0. Then we might try to factor that into some form like this. We're going to have x and x. This tells me the 2 signs are opposite. So I know one's a plus and one's a minus. This one tells me that the larger one is negative, and I think it's what? -3 and +1. This times this gives me -3. This plus this gives me -2, right? So now that we have it in completely factor form and it's equal to 0, we use the 0 factor property, which basically is saying either this guy is 0 or this guy is 0 or this guy is 0. If any of these are 0, then it collapses the whole thing to 0. If we solve each of these, we get x equals 0, x equals -1, x equals 3. And we need to check them by plugging them back into the original. We're out of time. I think I'm gonna stop here, but I'm gonna piggyback off of my type notes just for this one, just because we're out of time. So we got 0, -1, or 3. And with these, you definitely want to check because sometimes we get what's called the right-wrong algebra. Sorry, right-wrong answer. Algebraically, the algebra is correct, but sometimes we produce solutions that are outside of our domain and it doesn't work. So you always want to check them back in the original. I guess I can get rid of this other page. Okay. And so you see the results there, and I had to leave the other one as an exercise. Let me go ahead and make a copy of this available. Thank you. Let me make a copy of this available, and let me see, send the box. I think that was correct, but let me just make sure. Fall, College Algebra 1, this one, notes. So you can find a copy of this here, on Blackboard. When this bar finishes loading, you should get a copy of what you saw me writing. Are there any questions before we part ways for the day? Going once, going twice. Forever hold your P's and R's. Okay. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, take care. Peace.